You are a chemist, or at least you are for part of your week, otherwise you wouldn't be here watching this video. And like some chemists, you might want as much help as you can when it comes to moles. And today you will be getting just that, and this bridge here will help you. But before we walk across the bridge, we need to go through what we're covering today. So we are going to figure out what a mole is, why carbon-12 is so important, and then finally we're going to solve some molar mass problems. So here we go. This is what we're doing today. So a quick reminder to pause the video and download this PDF so you can be making your own revision notes as we go through this lecture. So we are going to start at the beginning. So we're going to be looking at what a mole is, but we're going to start at the beginning just below IB level chemistry. So this is to make sure that everyone is following along and doesn't get left behind. So for this, we are going to be using this reaction over here. So the reaction of calcium with hydrochloric acid. And this gives us the products of calcium chloride and hydrogen. So we don't need to worry too much about the why for today, so why this reaction is happening, how it happens as it does. We are just using this as an example to help us think about the moles. So in our example, we want to have an exact reaction. But what does that mean, to have an exact reaction? Well, this is the beautiful thing about the balanced equation. So yeah, the equation here is already balanced. So in this reaction, one calcium reacts with two hydrochloric acids. So we don't have a number in front of the calcium, but yeah, that just means one is reacting with two hydrochloric acids. And this gives us one calcium chloride and one hydrogen. So yes, the balanced equation gives us our ratio. So the ratio of how everything reacts. So yeah, so in this reaction, the reactants are in a 1:2 ratio. And then yeah, overall, the overall reaction is in a 1:2 to 1:1 ratio. So this means if I have one calcium and react it with two hydrochloric acids, I will get my products. So what does this mean? So does this mean I can go and get one calcium and two hydrochloric acids and react them together? Well, not quite. As what does it mean to get one calcium? How do I end up with one calcium? So what the numbers are referring to is a mole. So the equations don't need units, but the real world does. And the SI unit for the amount of a substance is the mole. So once we know what a mole is and how this links to measurements, measurements we can make, we can complete the reaction and get 1 mole of calcium, and then react that with 2 moles of hydrochloric acid. So what the mole does is it acts as a bridge. So this is why we've got the bridge here. So it acts as a bridge between the impossibly small world of the atoms to the normal size world where things make sense and we can make some measurements. So what the equation is really saying is that 1 mole of calcium reacts with 2 moles of the acid. But this is all well and good, but what is a mole? So all the mole is it's just a number. And that number is 6.02 times 10 to the power of 23. So it's a very big number. And as this number is always the same, it is a constant, and it is named after the person who helped to come up with the idea that chemicals react in fixed ratios, and his name is Avogadro. So here we go. So 1 mole is 6.02 times 10 to the power 23, and it's called Avogadro's constant, and that's what this symbol is here. So Na is the symbol for Avogadro's constant. So more on why it is this number in a bit, but the reason it is such a big number, and it is a very big number, it's to make up for the fact that atoms are just so small. So you need a mole of atoms, or getting close to a mole of atoms, before the measurements you can make become possible. It would be impossible in a school lab to measure out 1 calcium atom, or even 1,000 calcium atoms, but to weigh out 0.1 moles would be easy. Also, the concept of a mole makes speaking a lot easier as well. So instead of saying, can you measure out 1.3 billion, trillion, billion, million, billions of calcium, please, or whatever it is, you could just ask for a mole instead. So the mole, yeah, is a very helpful bridge that makes working with these teeny tiny little atoms a lot easier. But now to try and understand just how big this number is. So if you were treating yourself to a lovely beach holiday, you've earned it, and decided to count all the grains of sand on the beach, you would not even get close. Even if you had all the time in the world and went to all the beaches in the world, you would still not get close. Or if you had a bit of free time and a mole of paper in your magic cupboard, and you wanted to see how high you could pilot all the way past the solar system and still have most of the paper left over. Or even if you were as old as the universe and have been counting the seconds you are alive, 1 second per second, not only would you have a very dry mouth, you would have also counted less than 0.01% of what a mole is. So yeah, it's a big number, but it has to be this big because atoms are so small. Finally, as it is a number, you can have a mole of anything. But in the world that we live in, you can only really measure out moles of elements, molecules, compounds, ions, and electrons, which the IB is calling elementary entities. So yeah, elementary entities. Okay, so now on to what does relative atomic mass mean? So we'll get to our little definition here in a bit. So yeah, so relative just means in relation to something else. So yeah, carbon-12 plays a very important role in all this. Here we go. As all of the relative masses of everything in the periodic table are compared to carbon-12. So carbon-12 being the main isotope of carbon. So it was discovered that 12 hydrogens with their mass of 1 has the same mass as 1 carbon. Or another way of putting it is that a hydrogen has the mass of 1/12 of a carbon-12, which is our definition here. So yeah, so relative isotopic mass is the mass of a particular isotope compared to the mass of 1/12 of a carbon-12 atom. And yeah, so the definition is specific in stating isotopes and not an atom, as the masses of atoms is the average of all their isotopes. So all the elements' masses could be compared to carbon in this way, and they still are. So yeah, so carbon-12 has a mass of 12, or 12 atomic mass units, and the mass number for every element on the periodic table is stated in atomic mass units. But using the mole, we can connect atomic mass units to the real world, and therefore we can make measurements and weigh out some moles. So it was found that in 12 grams of carbon-12, there is exactly 6.02 times 10 to the power 23 number of carbon atoms. Incredible. Or to put it another way, in 12 grams of carbon-12, there is 1 mole of atoms. So yes, that's like really, really important stuff. So yeah, so because of this relationship, it now makes it possible to very easily measure out 1 mole of anything. So as carbon's mass number on the periodic table, is basically 12. So if we have 12 grams of carbon, we have 1 mole. And the really great thing is that this relationship extends to all of the elements. So if you measure out their mass number in grams, you will have 1 mole of that element. So we've got a bit of the periodic table here. So yeah, so if we measure out, say, like 19 grams of fluorine, we're going to have 1 mole of fluorine atoms. So yeah, and then the final thing is that the units for relative atomic mass are grams per mole. So let's go through a couple of examples. So yeah, already spoken about fluorine. But yeah, let's do fluorine as a molecule. So all of the halogens exist as diatomics. So that means fluorine is in fact F2. So fluorine in its diatomic state has a molecular mass, so that's quoted as Mr, has a molecular mass of 38.00 grams per mole. So yeah, so this is our unit here, gmol. So we can do the same with oxygen. So oxygen again is a diatomic, O2. So that would be, oh, not 16, it would be, yeah, 32. So 16 times 2, 32. And gmol. Yeah, so these are relative molecular masses. We'll just do some relative atomic masses, and that's just what it is on the periodic table. So yeah, so for boron, that would be 10.81 gmol. And let's go for silicon. So just taking these numbers straight from the periodic table. So yes, boron, boron, silicon, silicon. Nice and easy. So final thing for today is linking it all together and making things work for us in the real world. So back to our example of reacting calcium with hydrochloric acid. We know the ratio in which they react. So it's, they react in a 1:2 ratio. And that we know from the periodic table, we know the masses that would give us our 1 mole. So if we had 40.08 grams of calcium, taking into account its isotopes, that's going to give us 1 mole. Then the relative molecular mass of hydrochloric acid is 36.46. But yeah, we need 2 moles, so that's going to give us 72.92. 72.92 grams is going to give us our 2 moles of hydrochloric acid. And yeah, if we put that in a litre of water to give us our solution, they are going to react together. So we're going to go through solutions in more detail in a future video, but we're going to be focusing on solids today. So we know that if we have these 2 masses and we put those together, we know that the reaction is going to work. However, in reality, when you go and get a couple of pieces of calcium and put them on the balance, the mass is going to be much less than 40.08 grams. And the chances of it being exactly 40.08 grams is pretty much 0. So how can we figure out how many moles we have? Well, luckily, we've got this handy equation. So this handy equation links relative molecular / atomic mass to grams, which then also links to moles. So so moles equals the mass divided by molecular mass. So using this equation, it means you don't have to react whole mass numbers together. You can measure out a sensible mass, convert it to moles, and then get on with your experiment. So this is a really good thing because reacting whole moles together very rarely happens. So let's look at some examples of how to convert between mass and moles. Okay. So in our first example, we have our question here. So what mass of arsenic 3 chloride is produced when 0.3 grams of arsenic react with an excess of chlorine? So an excess just means we don't need to worry about the chlorine running out. So we're just going to be focusing on these 2 things. So first things first is 3 grams of arsenic. So we are going to be seeing how many moles are in 3 grams of arsenic. So moles is mass divided by relative atomic mass. And I've got the numbers over here just to help us out. So once you get, from your question, 0.3, so 0.3, you're just dividing it by its atomic mass, 74.92, and then this is giving us our answer. So that's 4.00 times 10 to the power of -3. So this is number of moles, and then the great thing about this, or the great thing about balanced equations, is that we can use the molar ratios to figure out the moles of everything else in the reaction. So once you know the moles of one thing, so the actual moles, once you've done your calculations, you know the moles of everything else. So we're only interested in the moles of arsenic 3 chloride, but because the ratio is the same, so it's 2 to 2, which is the same as 1 to 1, so this number is the same as this number. Let we go. So this is why the numbers are the same, because the ratio is the same. So now we know the number of moles of arsenic 3 chloride. We can then convert it to mass. So mass is moles multiplied by relative molecular mass. We've got the relative molecular mass over here. It's over here. And then, yeah, we get our answer. So just multiply those two numbers together, and then we end up with our answer. Happy days. So that's all there is to it. So you'll start to see a theme and a pattern arrive with doing these equations or doing these types of questions. So you're always converting something into moles, and then once you've got the moles of one thing, you know the moles of everything in the equation, and then you're converting moles back into something else. So in this case, we're converting the moles back into a mass. Okay, so now on to our second and final example. So with this example, we are looking at, we've got this question here, but we're going backwards. So we're starting off with the product. So we want 6 grams of our product, which in this case is the phosphorus 3 iodide. And then from that, we're going back to seeing how much iodine we need to give us the product that we want. But the steps are still the same. We're still converting to moles and then going back from moles to a mass. So this is the first thing that we're doing. So we're figuring out how many moles we have in our 6 grams. So how many moles in the 6 grams of the phosphorus 3 iodide? Well, dividing it by the molecular mass, which we've got given to us already, which is great to save us a bit of time. And then putting it into our calculator, and we are getting our answer. So 0.0146 moles. So that's over here. And then same as before, once we know the moles of one thing, we can figure out the moles of everything else. This time though, it's not in the same ratio, so we need to do an extra step, so an extra calculation, and that's what's going on over here. So we are multiplying the moles we have by our kind of conversion factor, so they're in a 3:2 ratio, and then we are getting our answer over here. So a good thing to check is that this number needs to be bigger than this number. And how do we know that this number needs to be bigger? Because 2 is smaller than 3, so you can do little checks along the way to make sure you're getting the right answer. So now we know the number of moles of iodine, and then our question is then mass of iodine. So the last thing we're doing is converting moles back into a mass. So we've got the number of moles, same as before. We have the molecular mass of iodine, and then we are getting our answer, which is in this case 5.55 grams. Happy days, nice and easy. And then just final thing is just thinking about significant figures. So because our question is significant figures in decimal places, so we've got 2 decimal places in the question, so our answer has to be to 2 decimal places. Okay, so that's all from me. Thank you as always for watching, and please remember to tell all of your friends in your chemistry class about these videos, and to like and subscribe if you want more IB chemistry content. Right, catch you in the next one.